Hello and welcome to everybody. I'm Professor Geoff Chase, and I'm sort of the de facto host tonight, perhaps only because I go last. So welcome. You're here at the UC Connect. Earthquakes plus innovation equals resilience. If this is not your flight, then you're still a chance to slip out the back or to stay and enjoy it. As a first up, a little bit of housekeeping. You are, as you will hopefully find out tonight, in one of the one or two safest and earthquake-proof buildings in Christchurch. However, should an earthquake strike, down the stairs first and then out, and no other order than that, in a calm, orderly fashion. There are gathering points in the square and around on both sides. Bathrooms or anything else, if you need them, are straight out to the back. And I think that is largely it. If you are feeling unwell or you feel like you're contagious with something, I'll be direct and blunt, please leave. From there, we have three speakers tonight. We'll start with Alessandro Palermo, and he will be talking about bridges and buildings and resilience, followed by Professor Rodgers about buildings and large structures, and this one in particular, and that resilience, and myself speaking on what's called structural health monitoring. And this all forms an overall picture about earthquakes. Earthquakes come, they commit a lot of damage. You'd want to mitigate that damage to be more resilient. Equally, and one of the biggest costs after the event was actually the indecision around how much damage was there. So a city is made up of buildings and lifelines, and Alessandro's talk focuses predominantly on lifelines. Geoff's talk focuses more on buildings, and mine talks about how you assess the impact, what happened, and what to do from here. So with that, I'd like to introduce Professor Alessandro Palermo from the Department of Civil Engineering. Please welcome Alessandro.
Right, or maybe I should go with this one. It's easier. All right. So good evening, everyone. So what I want to do is actually give a little bit of a talk, and with the title, actually show you that we can actually build fast and resilient. So, which sometimes is seen like one option or the other. And so what I want to do is to start actually with this picture. Many of you obviously have been through what I went through, and we are almost 10 years since the 22nd February earthquake. And this is like a bomb. You can see that an earthquake like the one that we had really completely destroyed our city. And the question that I think we will be asking ourselves, and I hope that you get some answers, is this acceptable? Can we accept to have another earthquake similar to what we had 10 years ago? And can we accept to have the damage and the consequences that have been paid and we're still paying for? And to me, it's been quite a challenge because I went through, especially with the February, an intense month doing reconnaissance, and this is myself actually standing there and watching the city completely destroyed. And unfortunately, it didn't stop with the Christchurch, Darfield first, then Christchurch, and then we have the Sedom earthquake, and then the Kakura. And I wonder, maybe it's my fault because I joined university in 2009, and so maybe I brought all the earthquakes from Italy to New Zealand. But I think what I want to reflect with this slide is this, that people don't care about earthquakes. In general, if you look at this graph, it's populations in billions, and in the last, this is 1975 and 2015, the yellow are the amount of population exposed to earthquakes. And the trend is going up linearly. So it means that people don't care about earthquakes. And in fact, we got twice the population living in the earthquake-prone countries. Then, if we think about building environment, which obviously goes together with people, same thing. People keep building buildings, bridges in the earthquake-prone countries. So in reality, if we like where we live, we think that we cope with earthquakes. We think that they may happen, and we don't care. That is really the fact. But the other important aspect is this. If we think about how the population is actually migrating, nowadays people want to live in mega cities, want to live in the cities because there are more professional opportunities. And what happened is that now it's what are the requirements, especially from the society, is to build fast. So you can't build a bridge and expect to disrupt, several state highways because it's costing billions and billions. Example, Auckland Harbour Bridge. We know what's going on, and this is an example of not sustainable traffic management. So the idea is that what I've been working the last 10 years is actually working on solutions which are fast to construct, but they're also resilient. And this is a project that's been funded by the MBIE. And the idea is that you build up concrete elements. I've done in buildings more on timbers elements. They're all prefabricated, and they are connected together with different reinforcing. And in a way, you can build everything very fast, a bridge or a building, and it looks like a big Lego system, where you put everything together. Usually when you see something like that, in the thinking of the earthquake engineers 20, 30 years ago, oh, you have a Lego system, it's very dangerous. Stay away from a Lego system if you have earthquakes. And what I'm going to do, I'm going to prove is actually wrong. So what I want to do is pretty much talk a little bit again about the introduction, what we learned, as Geoff was alluding before, what we learned from the earthquakes, and then I will show some examples of devices that will be developed, and then we'll talk about the connection, and I will look at the system, so the structure. In this case will be a bridge structure. So introduction and steel devices. So First of all, when we talk about we pretty much lived on our skin, is the first question is why we need to change the way we've been designing, why we need structures which are seismic damage resistant. I mean, it's a clear example. You've seen what has been happening in Christchurch, the disruption that we had. We need to do something different. And in a way, if we think about what happened in Christchurch, all those buildings has been designed very well, because they're all designed to fail to, in those parts, imagine this is the cross-section of a building, these are the beams, these are the columns, they're all designed to damage in a way that they dissipate the energy. The concept is the damage in the member is a way to absorb the energy of the earthquake. Obviously, if you look at from life safety perspective, fine. We had obviously 2 major collapses that caused fatalities, and this is bad. But if you look overall the performance, those buildings did what were designed for. The thing is that, yes, this is life safety. But as an outcome, you can see, this is Christchurch before, the garden city, and this is the car park city, because we know that we had pretty much car parks everywhere. Now it's better. We still have plenty though. But basically, as a result of that, most of those buildings couldn't be fixed. They were too expensive to fix. It was easier to demolish and build something new. And so this is not really sustainable. If we talk about sustainability, this is not sustainable. Imagine all the environmental consequences that we had to basically demolish a city. Where is going, for example, the waste, where is gone? So I think we need to start changing the way of thinking. Infrastructure was interesting because with the Kakura earthquake, 2016, although we haven't got major collapses of bridges, we had a similar performance. Most of those bridges in the area of Kakura, they had extensive damage in the columns. The columns are the ones who are taking the seismic forces. They are the legs. Imagine myself, I'm the bridge. The upper part is basically the mass. The legs are the ones who are taking all this wind coming from the earthquake. And so in the same concept, the columns damages, and the damage is absorbing the energy of the earthquake. But the interesting thing is that this is the new design, and this is the old design, the same. So the progress that we had in the last 40 years has been very minimal. if you compare with IT or what we have been facing, right? And so that obviously tells me, hey, we need to wake up a little bit, because the way we are designing structures probably should be changed. And this is an example of columns that have been tested a few years ago. Imagine that these are the earthquake. Imagine that you can actually be under a bridge, maybe it's not nice, and you have an earthquake, and then you see the columns going back and forth, and the intensity keep increasing, and as an outcome, you will see the concrete spalling, the bars will start healing, so going into a plastic domain, and it's what you want, because you want those reinforcing to dissipate the energy. But then, obviously, if you have something like that, you have also the danger that those columns can be maybe having residual displacement and start lining on one side, like the Pisa Tower, the beautiful Pisa Tower. I'm Italian, so I need to sell it, right? So, but we don't want that, because that is very difficult to fix. So, although we had all this mess, we have been always pioneering the earthquake engineering, and these are the 3 Ps, Professor Priestley, Professor Parker, Professor Pauly. And so, to me, they are the John and Lomo of earthquake engineering, for sure. But the target was always, obviously, the life safety. And that was the main target. And I think they did a pretty decent job on that. But the thing now we have to start asking is, if we have a structure which is damaged, what is the residual performance? So can the structure take further earthquakes, or do we need to repair it? If we have to repair it, how long will it take to repair it, and how extensive will be the repair? And obviously all those questions, these are the 3 main questions, are related with business, are related with the functionality. So now we are thinking, if we can guarantee the life safety, we need now to be able to design those structures to maintain the functionality, because you don't want to have business disruption. And so this is an interesting survey from Yokohama National University in Japan, where for bridges, the society had very high expectations. They expect that a bridge should be immediately open after an earthquake, and if there needs to be something done, it has to be within 1 week, because obviously is a public structure. And imagine if you have a bridge collapsing, it gives like a sign of vulnerability for the entire network. I'm selling bridges because I do research on bridges, of course. So bridges are very important. But now, what do? Shall we call our superhero and say, hey, we need to turn all this mess into resilient bridges and structures? I think what we need to do is try to change the way we think and try to, yes, accept the damage, but be able to repair it. And so when everyone talks about resilience, the definition is simple, right? It's the ability to bounce back in an unexpected event. Usually it's a bad event which affects our lives. We have our performance. We can have our performance measured in terms of professional activities. And let's assume that we run always 100% for our 70, 80 years of life. But what happens when we have something bad that happens to us, we have a loss or something, we drop. And then we say how resilient is a person. We measure in the ability of this person to come back and be functional again. And this is my personal human resilience curve, which has been hit quite a lot in 2018 because I lost my mom. So if we try to now go into the engineering side, what we can see here, we have, when we talk about resilience, we have 3 R. Robustness, which is reduce the probability of failures in any component of the building. Then we have repairability, which is linked with the consequences from failure, so reduce those consequences. And then recovery, so the time. Be able to recover very quickly. So ideally, if you have an earthquake, you would like to have these always 100%. It basically means that after the earthquake, say, oh, it's just a magnitude 10 earthquake, doesn't matter. It's just a little bit of shaking, right? So in a way, I like that we are doing this presentation all connected with the 2 Geoff, because the idea is that to increase this resilience, this curve. If you have an earthquake, a normal structure will be hit down, and then will take some time to go up, and this will be the recovery time to go up to 100%. In reality, if we develop new solutions which are controlling the damage, and then we know how to repair these structures, that curve will become far better. But, and then Professor Geoff Chase is going to close up, if we add sensors in the structure, we will instantly be able to say, hey, that structure is fine. And I don't understand why we don't put sensors in our structures, why we have an accelerometer in the iPhone, and we have 200 sensors in a car. I can't understand why we can't think to have sensors embedded in our structures. And so the idea of developing these new solutions is actually that traditionally, you can see, imagine that is the earthquake, you've seen in the columns, you have damage in the member. With those new solutions, we basically don't have any damage in the column, and we, in reality, have the connection designed in a way that they actually dissipate the energy. And so the green elements are the fuses, are the ones who are taking the energy. But they are placed outside of the member. That basically means they are easy to repair. What do we have inside to avoid the Pisa Tower? We have a rubber band. No, it's not really a rubber band, but high-strength steel, which keep the structure up in place. If you lose the rubber band, you are in trouble. Boom. You don't want that, right? So I can, where is Jess? Jess, you need to pass my toys around. So if you want to play with the rubber band, that's an option. But the idea is amazing, because this idea, which is simple, you put these high-strength bars which are recentering the structure. The fuses that are dissipating the energy can be applied to any structure. Can be applied to a building, to a bridge, but is independent of the material. This is a concrete, this is a steel, and this is a timber. And again, imagine those rubber bands. No, that's weight. Imagine those rubber bands, again, placed, in this case, within the columns, within the beams, and running through. So now, when you design those elements, those connections, what is important is control the strain in the materials. But we can do very easily. Then minimize the potential residual deformation. We don't want to have a Pisa Tower, and we have the rubber bands. And then make sure that we can repair very easily. So if, for example, and then Jess is going to pass those 3D printed devices, if these are placed externally, will be pretty much easy, and knowing that we need 4 or 5, 10, 100, will be easy to replace it because they're placed externally to the structure. And the key thing, especially for bridges, we need to make sure that those elements don't actually rust. So we need also, we've done research on that side. Maybe, Jess, if you want to pass those devices, that would be good. So these devices are called Jack, should come back. So that is a joke, but it doesn't work. So now, the thing here, I put the pizza because these are 4 ingredients. To have a beautiful pizza, you don't need to put a lot of ingredients. You know, I'm an Italian, I can sell it well. The dough, the mozzarella, tomato sauce, and basil. This is what you need. So now, what now you need to think about, this is an example of called in timber press lamp system. This is a beam column joint. This is a young Hunter house in Victoria Street. And this is the typical connection. After an earthquake, this is what you expect. You will be in a position to replace those devices if needed. So these are the dissipative fuses. So I will just briefly talk about this device, and then Professor Geoff Rodgers is actually going through and spending a lot of time on that. But the idea is that those are just simply pieces of steel, and they have a tube outside. I think Jess has passed the samples around. These are 3D printed samples. And the tube is just preventing them from buckling. So the idea is that when these devices goes in compression, they don't buckle, okay? And the performance of those devices, they are done in a way, steel is actually elongating a lot, is actually absorbing the energy of the earthquake. And the idea, this is just pulling back and forth, is simulating an earthquake. And the idea is that if you have a big area, this is a force and this is the displacement we're measuring at the top. If you have a big area, that means that the device is quite capable to absorb the energy coming from the earthquake. So the application has been extensive, not only on bridges, I will show you a bridge example, but in timber and concrete buildings. And if obviously you are all from Christchurch, if you go Victoria Street, you can start from Knox Church. You can't really see them, they are hidden at the bottom of the concrete columns. Or then if you pretend to buy some expensive Italian furniture in Matisse, then you can go inside and you will find all the detailing of those devices. So we had few applications, and what I want to mention that those devices are also being placed in the Kaikoura District Council in Kaikoura. And this building actually went through the Kaikoura earthquake, so it's very, very close to the design earthquake level. And the building was used as a headquarter coordination center during the earthquake. So that means that we had also some real proof that actually the building performed extremely well. So I will run through very quickly another device that we have been developed. Not actually the concept of the plate itself, it was developed by Dr. Ivan Skinner, but we actually, the packaging we came out with. So the idea is that you have these curved steel plate, and when you put two elements, like two walls going like this, the steel plate will start rolling. And their rolling movement dissipate the energy. Very clever, because it's just a plate, it's very, very cost effective, and is also easy to replace. Here, there's just the details, concrete, timber, and steel, and this is Southern Cross Hospital, this is Nelson Marlborough Institute of Technology, and this is a building in Cambridge Terrace. So very, very easy to install and to remove after an earthquake. And the idea what we came out with is actually to package up those steel plates in one big bracing. Now you see now Christchurch is the bracing city. We have braces everywhere, you know, even through the windows, which is terrible. And but the idea is those braces are dissipating the energy. So what we have here, we have this casing, and this casing have been then applied to bridges, especially this one, the small one that inside contains these small plates. I think Jess, where is Jess? I have this small toy that you can pass it around. Bridge connection. I need to go a little bit faster. With the idea of the bridge connection in the program, in the research program, we tested different connections. And to pretty much summarize the slide is this. We tested the prefabricated columns, all fast construction, but one has very high damage, and this one is low damage. So where you have minimal damage is high performance, is like high speed, Ferrari. Where you have high damage, low speed, Corolla. Great car, by the way, but just giving the example. So the low damage connection is the Ferrari, is pretty much interesting because it's what I was describing before, is a solution where you don't damage the column, but you only replace the devices. And so what we did several testing, and we started for a bridge prototype, and then we tested just the substructure of the bridge, which is the one which is actually taking the earthquakes. So this is imagine that this actuator is actually simulating the weight of the deck, you know, all the bridge girders on the top. And this one is actually simulating the earthquake, pushing back and forth. Inside there is our famous rubber band, high-strength steel. And these are the devices, the one with the U-flexural plate, and this one with the axial bar device. And you can see inside there is this element, this bar, which is actually bringing back the structure to the original position. So the beauty of this is that after the earthquake, you have only to replace the bar. So this is the performance, again, damage, Toyota, Ferrari, no damage. So I'm just selling Italian brand, sorry. So we're now moving in the system performance. As you can see, the connection has been, we started with the device, we moved to the connection, and now we're looking at the system. We did a lot of testing, and one big test that we had was a test with the full structure, 2 span bridges. This is simulating the abutment, and we did all prefabricated. This is just to show you that we built and tested a bridge which was built fast, but also with resilient solutions. And this research led into the application where I want to spend 2 minutes and just talk about this amazing application that we have here in Christchurch. So is the Wigram Magdala Bridge Link, which is located not far away from the university, and it's been opened in 2016. The designers were Opus International, WSP, and I have the pleasure to be involved as an external consultant. So what I want to say, this bridge is the first adopting that innovation, but I think the innovation is not just the technical innovation. In this particular case was people innovation, because we started in 2011 a Canterbury Bridge Group that now is recognized as a CSOC Bridge Group, and we had a lot of interaction with Opus, the designer, the client, City Council, and university. And we have more than 10 labs too, and that created a seamless interaction between the three, among the three. And so when we had the opportunity, they wanted a Ferrari. There was no question, we want a Ferrari. So obviously, the bridge has some complexities, and I think we don't have too much time to go through, but it's a small bridge, almost 100 meters long, with 3 spans, and the NZTA wanted, because there was another estimation of the vehicles passing through, wanted to increase the importance level of the structure, which means that the forces going into this bridge is going to be higher because it's more important. And as a consequence of that, the idea was to implement that solution that I was showing the testing before into this bridge. Now, let's be honest, it doesn't look a Ferrari. This is more the engine of a Ferrari, I would say, because you can see here, it looks like a conventional bridge, but inside there are the rubber band, which are unbonded and post-tensioning bars, and the devices, which are the fuses, which are dissipating the energy, are embedded in the pier, in the foundation, and in the top of the beam. But they are easy to replace, okay? So the detailing are exposed here. The bridge has already the foundation built, so they have to build the foundation of the foundation. And this is the detailing, and the complexity of the detailing was given mainly because the client didn't want actually to see the devices exposed. That was a particular request from the client. While for buildings, the devices are actually an architectural feature that actually the clients want to see. So these are details of the construction. The column had was a steel column that then was filled in with concrete, and these are the devices embedded in the foundation. And so these are details of construction. This is the duct where inside there is the high strength bars, which helps to recenter the structure. And then once they've done the piers, then you put the bridge girders on the top. So almost finished. The bridge obviously has been recognized by Hassens, and then had been also got a commendation from the New Zealand Concrete Society in 2018. And just recently, we put a research paper to the journal American Society of Civil Engineering, and it's been awarded this Alfred Nobel Prize because it was a good paper. But I think the key sell of that paper was actually the final part, which actually the paper was talking about that bridge, which was recognized quite a novel design. It almost finished. I think you will think, oh wow, that job done. Now we have all the solution. The thing is now we have to implement the solutions. And this is like the following step. It's not easy. And Geoff will tell you about working on this building and working on other buildings, how difficult it is to implement something new, because everything is new is a risk. And everyone wants to stay away from risk. And I think to me, yes, we have a lot of those toys in the city, but we should have more. That is clear. But the main thing for bridges is that we need to start thinking a little bit broader, right? We shouldn't think that resilience is the new sustainability, from my point of view, especially if you think about bridges. Because if you use conventional materials, they are going to rust. They are going to have problems of maintenance. An example is the Morandi Bridge in Italy. It collapsed in 2018 because it was mainly due for of the problem of pure maintenance. And so what I'm working now is using glass bars, and I have one PhD here working on that, so you can, if you have questions on these, Jess, if you want to pass around. And these are no corrosive materials. And then you should have already received a couple of blocks, concrete blocks. One is ultra high performance concrete, which has a strength similar to steel. And then there is another concrete block which has rubber. And that is waste rubber coming from the tires. So I think we need to start thinking to incorporate novel material to improve the sustainability of our infrastructure, and possibly combine that with digital engineering and digital fabrication. And I just close with this slide saying that we really need to make a change. This was me in 2018, Los Angeles, Skyline, and this is Blade Runner, one of my favorite movies, the old one, which was projecting the buildings in the future, 2019. So we need to wake up, guys. So that will be next episode. Thank you very much.
We'll be taking questions at the end, so save them in your head or write them down. I'd like to welcome Professor Geoff Rodgers up to the stage and talk about his work on buildings and building resilience and energy dissipation.
Thanks, Jeff. So, yeah, my talk's going to follow on. I thought some of the similar concepts to Alessandro, and then just applied to some different structures. So, the Christchurch experience, obviously, it hasn't really been considered possible conventionally to design a building to remain entirely elastic. Essentially, the concession has been made to accept that some damage will have to occur, really just through economic aspect of the building and just not knowing exactly what the ground motion will be. There's a huge amount of uncertainty that side of things. So essentially the traditional thinking has been to accept that some damage will occur and to implement a hierarchy of strength within the building as to where that damage will occur. So the idea there is the horizontal beam will actually yield or give way at a force less than that which will create damage in the column. So go back to Alessandro's analogy, if you do damage my leg, I'm probably going to fall over. If you damage my arm, I'm not going to be happy, but I can remain standing. So that's all about maintaining the integrity of the building, preventing collapse and saving lives, which, for other than a couple of tragic exceptions, that design approach worked pretty well at saving lives in Christchurch. The trouble was, though, the demolition which followed. So that isn't actually a unique story globally. Obviously, the $40 billion damage bill in Christchurch is something we're all very familiar with. But there's also earthquakes such as Northridge in LA in 1994, where there was an estimated cost of $40 billion US. Kobe, Japan in 95 with $200 billion US, and Shishi in Japan and Taiwan in 99 with $20 billion in damages. So not a globally unique story, what we've seen here in Christchurch. So essentially, we can't predict when and where an earthquake will occur, and we don't know exactly what that earthquake will be. The one thing we do know is it won't be the same as any earthquake we've seen in history before. So what we do know, though, if we look at a lot of earthquakes in aggregate sense, they do have some same broad concepts to them, whether it's a near fault, whether it's a far fault, whether you're on soft soil, whether you're on hard rock. All those factors have a significant influence on the way the ground will shake. But there are some broad similarities between the earthquakes. So this is actually 20 different earthquakes here plotted and overlaid. So there's significant variability there, but there is some similar characteristics. So this is actually what we refer to as a response plot. Essentially, it's the period of the structure and how much it will react. Classic dynamics thing is that if you shake something at its resonant frequency, it will respond with large amplitude. So in any engineering problem, you want to avoid driving something at its resonant frequency. So on the the right-hand side, we have a sort of taller, more flexible structure, which will be a long period. And on the right, we might have a shorter, squatter, more rigid structure with a shorter period. And that shorter period structure just happens to fall into the range where the frequency of ground motion, within the ground motion, there's frequency with much larger content of that shorter period. So that is actually one of the big design challenges. So if we take a structure that's reasonably flexible, it might be reasonably well to the right on that plot where the demand's reasonably low. But if we just stiffen that up, we actually move left on that demand curve and actually increase the demand as we go along. So one of the issues there, this was it was a classic example of this was actually the design of the South Ringa rail bridge. This was back in the 70s. So they essentially did an initial design. This was a tall pier. It was reasonably flexible. Ultimately found out it wasn't strong enough, so they iterated on the design, put more steel and concrete into it, and then found that actually, even though they'd strengthened it, because of the fact that they'd moved further along the design curve, it was still not sufficient. So they moved further along and ended up in a sort of iterative design thing where they often referred to in the profession as sort of chasing your way up the demand curve. So clearly that was actually a young engineer by the name of Ivan Skinner who overheard this discussion and said, well, why don't you let it rock? Why you've sort of found yourself in a thought trap where you've started down a path and actually maybe re-challenge your assumptions. So if we plot that differently in terms of a design code, if we have the more flexible structure on one plot, so a radial line represents a period, essentially, and then the more rigid structure is up there with larger demand, the way a traditional building will perform is sort of having an initial period when it's elastic and everything's sort of behaving as you'd expect under small earthquakes. And then once the demand gets larger, we actually see that onset of damage, that damage occurring in the beams and the softening of the structure. So that actually has some really, the damage itself causes lots of problems long term in terms of the need for demolition and repair, but it actually has some really favourable aspects in terms of the way the building interacts with the way in which the ground's shaking. So by the building softening, undergoing that damage, it actually lengthens in period and it moves to a more favourable part of the frequency content within the ground motion. So the key thing there, though, is that transition from one initial period to another period has traditionally been this onset of damage. And that obviously has the implications that you can see out the windows here. So onset of damage is great, and it reduces stiffness, lengthens the period, and reduces the demand. It reduces the accelerations felt by the occupants and the contents, and it also absorbs a significant amount of energy. The trouble is, though, that the building may not recenter at the end of the earthquake, and there'll be significant cost of damage and downtime following the earthquake. So the thing we would say is, what if we could have the first three without the last two? And that really is the underlying premise behind the dissipative rocking connections. So essentially let the structure move and deflect in response to ground shaking. So if you're in a boxing ring, the worst thing you can do is stand up and directly take the punch right in the face. If you can move and deflect with that, you reduce the load that you take. So this is, you've already seen this sort of Alessandro's slides. We're actually talking about a very, very small amount of rocking here. You know, it's only on the order of a couple of degrees, but in terms of the duration of different pulses within an earthquake, it's actually really, really important in terms of how the building reacts. The key thing was there that if we take away, all that damage, all that destruction, does absorb a lot of energy. So if we take away that, we need to provide something else in its place to try and control the way in which the building responds. So there's a whole suite of ways you can approach this, but one of them is looking at, say, an extrusion damper. So this is a lead extrusion damper. It was something that was initially developed, the concept was initially developed in the 70s by Bill Robinson and some of his colleagues at the DSIR. They were also the same guys that developed the lead rubber bearing. And essentially, if you take Play-Doh spaghetti and you push down that lever, it squeezes that Play-Doh out through that orifice. That's the process of extrusion. And as you push on the lever, that's a lot of work that you're doing, and that energy is absorbed as that Play-Doh is deformed. So the key there is that we basically do that in a reversible way, where either the constriction on the outer tube or the bulge on the central shaft, as there's relative motion between those two, we essentially have a moving orifice where we're forcing that lead from one side of the bulge to the other, and that absorbs a lot of energy through heat. So They can be very compact, 12 to 25 ton resistive forces. Another thing we've looked at, I won't go into a lot of detail here, but a lot of the commercially available viscous dampers for structures, because you can buy viscous dampers for structures, much like the ones that control the motion of the wheels in your car. Most of the commercially available ones tend to be quite a basic damping behaviour. Whereas if you look at a high-end mountain bike or perhaps a Ferrari, if we're going to use Alessandro's analogy, you have much more complicated damping behaviour there. So the compression, the rebound, you have asymmetric behaviour, you can have different behaviour based on velocity, and some of the work we've done has also looked at incorporating those same sort of characteristics to have a more high-performance viscous damper to fit into structures. Essentially, we can have quadrant-specific, whether it's going outwards, whether it's coming back. There's a whole lot of different aspects there that need to be considered. So what I'm going to cover here is some shake table testing that was actually done at Tongji University in Shanghai. So this was my Christmas in 2018 and into the new year. They essentially have a large shake table array. There's 4 individual tables that sit along a long trough. It's designed to give them the opportunity to create model bridge tests, and it can also be used for building tests. So in some ways, this actually gives you a real feeling on how insignificant we are as humans when you look at how much energy and how hard it is to recreate shaking on one building. This is the basement of that. It's a huge range of hydraulic pumps and accumulators. And this is one of the plates on one of those pumps, 380 volts, 656 amps at full load current. About 250 kilowatt per pump, around about 3 megawatt that this thing's drawing, or around about the same as 2,000 houses just to shake one building when the fault rupture actually shakes thousands all at once. So this is actually one of the buildings here, and you can see a person standing here. There's a person standing in the control room here. That's Ichu Liu. He's a former postdoc at the University of Auckland who we're collaborating with on this project. So this building is about 9 metres tall, a footprint of 6 metres by 9 metres, and it was about 140 tonne. So we used rocking walls as well as some slotted beam column connections here that were developed through some testing at Canterbury about a decade ago. So this is... We should actually give you a warning about some of these do sound a lot like the earthquakes you've lived through, and one of my colleagues made the point that I probably should actually warn people that that visceral reaction, that hair standing up on the back of your neck, is you listen to these loud, it does bring back some of the less favourable memories of Christchurch's past. So this is the same building from another angle, and so it is a big shake table. That shake table alone is worth about 30 million New Zealand dollars, so it's unfortunately not something we have the capability of doing onshore here, which is why we end up doing this in Shanghai. So this is actually the rocking wall. So the rocking wall actually sits recessed down into the foundation in a steel pocket. So that steel pocket prevents the wall sliding, it constrains it to sit in the base where it should, but it can actually uplift. So you see some relative motion as the wall uplifts, and then this is actually 3 viscous fluid dampers mounted between the foundation plate and the wall, and that provides damping to the structure as the relative motion occurs in there. So as I said, the relative motion is actually pretty small. It's a reasonably modest uplift, but it has a significant impact on the behaviour of the structure. This is the same thing there with actually some steel fuses, as Alessandro discussed. So that's following a design that he'd done a lot of work on prior. And then it's just basically damaging that steel component in that case to provide damping to the building. So the obvious question is, that those dampers are actually a pretty small part of the overall structure. So the question you might have is, well, how much influence do they have on the overall response? So the last test we did, at this stage we're about the 6th of January, we'd done all the tests we really wanted to push some demand into this building, understand just what some of its limitations were. So we essentially took all the energy dissipation off it and we just shook it as hard as we could. So this here was it's actually the same ground motion, the same structure as you saw a couple of slides ago, but this time without the energy dissipation in it. So, I guess you get the idea that was a significantly larger response and it took significantly longer to come to rest. So your life was never at risk had you been in this building, but it wouldn't have been a particularly pleasant experience to be in there. So just for comparison, the blue line there was the same structure with the same ground motion with the dampers installed, and then the orange was without. So a significantly larger response and a significantly longer time to come to rest. So the next thing I want to talk about was Turonga, the building that we're standing in here. So it's a steel frame to carry gravity loads throughout the structure, and then a couple of three reinforced concrete cores that take the majority of the seismic load. So one of them is this area right over here, covered in the nice wood veneer. So that's actually this one here that you can see in here. And there's coupled rocking walls. They have U-shaped flexural plates between the two, as Alessandro talked about. So at the intersection of the two walls, they rock independently, and then there's UFPs mounted between the two walls to provide energy dissipation. One of the engineers at Lewis Bradford, so Tim Shannon, was the principal designer for that, and also Dr. Jamaluddin Bazoui. So he was a University of Canterbury PhD student, working with Geoff Chase, myself, and his primary supervisor was our colleague Greg McRae in civil engineering. And his PhD was actually on low damage column base connections. So like this column here, you can see the white one, where that meets the foundation is actually using a design detail that he spent 4 years testing extensively in the lab to prove that concept, and then got used in this building in addition to several other aspects. So that was an incredibly satisfying thing to be involved in. So this is one of the lead extrusion devices mounted within the building. So it's actually in this stairwell just here. So it's a service stairwell, it's not the primary way out, but that's at the ground level, just one level below us there. So that's the lead extrusion damper to provide energy dissipation during relative motion there, just like in the video you saw before. The building has won quite a few awards from New Zealand Society for Earthquake Engineering, Structural Engineering Society, Association of Consulting Engineers, and Concrete New Zealand. And also late last year, it was awarded the Extreme Conditions Award by the IStructD, the International Structural Engineers Association in the UK. So it was the only building or structure in the Southern Hemisphere even shortlisted in any other category. So it's quite a significant award, sort of kind of regarded as as nominally the world champs of structural engineering, and it's the building that we're in right now. So that's a huge honour for me to have played one small part in that project. Another project that came about, this was actually talking to a Berkeley-based structural engineer at a hotel reception during a conference in Nara, Japan. He essentially had this problem where he was building a community housing project. So this was a place called the Mission Economic Development Agency, MEDA. They essentially built housing in the San Francisco Bay Area, and they had this project in the Mission District, which is sort of south of the city down towards Silicon Valley, and it was looking in the direction of Silicon Valley. It was looking at basically low-income housing. So 25% of the occupants of this building are formerly homeless, and the remaining 75% are those that live sort of below half the median salary for the area. So you had this problem where any non-profit, any charitable organisation that builds community housing has this issue that they can't really spend a whole lot more, because if they did spend more, they could just put that money into additional housing. So immense need and not enough funds to service that need. So ultimately what ended up being implemented there was a rocking foundation detail. So it was actually, the rocking interface was actually moved slightly lower. So rather than at the structure to foundation level, it was actually moved below that between the foundation and the pile. and the damper was mounted between the top of the pile cap and into the foundation. And that was a project which, that's the completed building there. It's not been professionally shot because of the COVID issues in the Bay Area at the moment, but so these photos aren't as they perhaps could be, but that's the completed building with people inside it. So the key thing there is that it did require quite a lot of innovative thinking to try and achieve the resilience without a huge cost premium. So I guess when you think about this, a lot of the time you think about seismic resilience, you might think about a hospital or a server farm or some really high-end infrastructure. But in this case, it was really about trying to compensate for the lack of personal resilience for those that live in this building because of the underprivileged background that they come from. And realising that if that building was left inoperable or couldn't be occupied post-quake, a lot of those people don't have a good social network around them. They don't have a lot of support. They don't have a lot of personal resilience. And there's a good chance some of them might end up back on the street. So then that actually made the resilience of the building that much more important. So the total premium was about $100,000 on a $42 million build to go with the alternate design. And that was actually awarded a gold rating from the US Resiliency Council for the performance, the predicted seismic performance of that building. So quite a significant achievement, and really largely due to a committed range of architects and engineers and everything that worked on that building. So great project to have been involved with, and I'll just pass across now to Geoff.
All right, so I'm here to talk to you about something perhaps a bit more futuristic. And we've heard a lot about monitoring damage or mitigating damage, how to make damage a lot less. We've seen a lot of catastrophic pictures of major damage, and figuring out major damage is always easy. But first, let's go back in time. So about 34, 35 years ago, I started my career at a place called General Motors doing energy dissipation. Alessandro, you and I will have a conversation about the lack of energy dissipation in Ferraris afterwards. But not too many years after that, just got to defend my home turf. Not too many years after that, I was sitting 9 floors up at Stanford University studying for pretty much the first test of my master's degree in, believe it or not, structural dynamics and earthquake engineering. And you hear that sound, that running feet sound. What the hell is that? Shortly enough, you find out it's Loma Prieta, a large earthquake that came rattling through. So, we dutifully got out of the building and we were waiting outside, and about 2-3 hours later, it's dark now and all of us are still standing outside. And a truck drives up. It's got the Stanford University logo and there's a couple guys inside. And on the side of the truck, instead of a big rear view mirror, outside wing mirror, they've got a spotlight, not a small spotlight, large spotlight, almost the size of a basketball. And he shines it up and down this 12-story building from about 50 meters away. He goes, yeah, that'll do. That's damage monitoring. All right, so perhaps we could do better than that, just a wee bit. So I'm going to talk to you about the future of damage monitoring and how really it should be done and how we have developed that here. And in particular, it's about the ability to know. So buildings get built, they go through an earthquake, they're damaged, sometimes more than we expect. Sometimes they weren't constructed quite the way we expect. The heart of Stanford is a massive sandstone quad. It's a heritage structure, or set of structures. And it's been repaired, of course. But when they went through, they had the old building plans from just after the 1908 San Francisco earthquake. And they found that the buildings were all built generally quite well. Not according to the plans, but generally quite well. So you can have all sorts of issues beyond the fact that buildings are, for the most part, designed to fail, and in failing, protect lives. The question then, a big earthquake rolls through, things look fine. How much? Can we get something better than a couple guys, spotlight, and they don't say she'll be right in America, but big she'll be right. So that's what we're going to talk about here. So the very unexciting why, I don't think I need to cover this at all. I think we've heard about that. But you can count the little dots. There's 20,599 of them. But nobody wants that. So we are world leaders, and I think you've already heard about this, in aseismic device design. So a series of devices. There's Kilmore Street building up to the side there. Nobody should trust me with technology. And the Forte Health. This is a base isolated structure, the Christchurch Women's Hospital. Too wrong.
5 minutes time. Please make the way to the exit on the ground level. Thank you.
All right, you still on the same flight? Okay, good. So we are experts at this. Base isolation is a concept that was invented here. These high force of volume, these ultra low cost devices that Jeff Rodgers just talked about were invented here, and so on. Damage in history, they matter. What if it goes unseen? It's unseen damage that'll take you down. We have CTV. We have a range of events. And each of these events, September 8th, and a major aftershock within about an hour, 5.1. Other major aftershocks after that. February 22nd, 21st, you had a major aftershock within 45 minutes, almost the same size. The same in July, and again in December of 2011, although that was 3 hours later. So here's a question. A big event is rolled through after maybe some prior big events, and you've evacuated the building. Should you go back in and get your stuff? Can you? You left your wallet, your purse, your phone, the center of all modern life. Should you? Is it safe? What if that next aftershock rolls through? How damaged is the building? These questions matter, and you'd like some precision, and you'd like an answer now. Where and when in the culture that I grew up in or around, there was a phrase, hey, I got a guy. And the answer here is that there are engineers, men and women, who will come out and they will inspect that structure for you, next week. What do I do now? So we're going to talk about structural health monitoring, or SHM. And it's really a simple set of technologies. Simple sensors. You mount them perhaps on every story going up the structure. And you want to do a bit of filtering. You're going to identify damage and changes. You'll have some definition. And out will come, where is it damaged, at least by floor? How much is it damaged? Does damage even exist? So building plus sensors plus computation and software. It's a modern business plan. We all pay for subscription services now. I think if I asked who here had any of Netflix or Spotify or Amazon Music or a range of other systems, I would get pretty close to 100% buy-in. So there are a lot of limitations in the way it's done typically and today. In particular, that you have the structural health, the damage monitoring comes, afterwards somebody inspects it. Now, of course, if it's this damage, it's pretty easy to know not to go back in. But we don't have optimized decision making. We don't have a quantified output. We don't have a number. And in particular, you'd like to know, if I could do the structural health monitoring, well, and there's a lot of mathematical research on this, it doesn't get you too far. What's going to happen next? So great. My building is damaged. If a big aftershock rolls through, will it be a little bit more damaged, a little bit less damaged? How stiff is the building? So Alessandro's toys are still circulating through the room. You want the building to be stiff enough so that it can move and absorb energy either through devices or through absorbing energy in the beams, but not too stiff. Otherwise, you're shaking a carton of eggs. All right, and so bad things happen either way. Equally, when it moves and you have that damage, how much? In the cases and the pictures we see catastrophically, it's always huge. It's an easy answer. But most of the time, you can't see it. And you'd like to know, what is the future damage or collapse capacity? What is my risk of collapse? Should people come back into the building now, next week, after repair? Never? What are those answers? All right? If you knew the structural status and the structural stiffness of the building, if you knew it, you had a number. We're all very good with numbers in the engineering profession. You could do some modeling, and then you could assess that risk, and you could provide a number to a decimal place that I wouldn't trust, but certainly you could provide a number like 70%, 60%, and over a period of time. And you could trade that number off, and you could look at the cost of retrofitting with some of Alessandro or Jeff's devices versus the risk of collapse and how much it would change, because you'd have a model. You'd be able to assess all of this information. And I ask you to imagine, and I hate it when people say, imagine a world where, but imagine a world where you could know that, within 10 seconds of the end of an event. 10 seconds. You get a text. Don't go back in. The building owner gets a text. you're in deep trouble. Well, with a number and a risk. All right? You could put numbers to those risk thresholds. Above or below a certain threshold, no one's allowed in the building, not even to get their personal items. What if we can make this all automated and easy so I don't got to need a guy? All right. So what we're saying is we especially don't get good information. $40 billion we've mentioned. That's about 1.5% of GDP at the time. 8 years or more. Typically, it's about 10 to 12. Capital, some insurance issues and other liquidity issues in New Zealand means it might be longer. And that's just to rebuild. To get your economics back is often another 10 years. People go, we're going to rebuild soon. When will this be done, Jeff? And I'm like, is it 2022 yet? I mean, I don't even want to think about it until then. And really, you're talking about 2030. All right, so it's important to have resilience. I think we all knew that, but there we go. A 1% cost savings on that, or less, is 200 to 400 million back into the economy. Just 1%. 1%, which is a nothingness if you have good information. Right? You look at businesses today, modern businesses are very much about information services, and they're making a heck of a lot more money than, or saving people a heck of a lot more than the 1% and making more than that. So there's a huge lack of good information, and this talk is entirely about how to use some very cheap sensors and a bit of mathemagic and turn that into very good information. So what if there's the old sort of SHM, people are sort of good at analyzing things after the fact, often with a human in the loop, and I won't talk about the methods or the math today. And that kind of gets you up to where we are, and you can create damage indices based on the amount of motion. But then, as I said, what happens when I go forward to the future? And particularly a predictive digital clone models. Digital clones is a hot word. I would call it a virtual building model. But if you listen to the commercialization people, Gartner's is a major firm that surveys technology trends. The last 2 years, digital clones and what they call hyperautomation are the #1 trend. By 2025, this is a $100 billion a year business. It is already a $20 or $30 billion a year business. By 2030, it is $350 billion a year globally. Many of us will perhaps remember that a number of years ago, a Malaysian Airlines plane went off track and was found, or pieces of it were found, that probably crashed somewhere in the Indian Ocean for reasons still unknown. But that was way far away from where anybody would have ever guessed. And here's how they found out. General Electric, who own Pratt Whitney, an engine maker, they make digital clones of their engines so you can optimize the life cycle of the engine on that plane, which is a massive investment for you as an aircraft and an airline company. And that is sending data back in bursts to satellites, even if, like Malaysian Air, you hadn't bought that service. It's still sending it in bursts. And it was from those satellite bursts and which satellites, they're able to say, well, actually, you're looking over here, but actually, maybe it's way over there. And that led to that change. Digital clones, it's big business, will be much, much bigger business. So this is our vision of the future, and the idea is that you have real-world conditions, data feedbacks, and computation. You make a digital clone of the building. You can monitor that. You have smart connected products and services. Predictive operations, alert, advise. Do you need retrofit? Is your building responding unexpectedly? What is the risk? What is the number? Give me a number. There's a 20% risk this will collapse if you have an earthquake aftershock over 5. Unacceptable. All right, we're going to put numbers to these kinds of things. We're going to show you how we do it and that we have that capability. This is really the boring version. It's lots of words and things, just 3 key elements I want to talk about. You need a simple structural health monitoring approach to assess the damage I have now. One that can assess the damage in terms of stiffness. It can give you a reduction. You had 100% or some value of stiffness here, and now you have 40% less, whatever that number might be. I need to be able to have it that it's automated, that I can take sensor data and it runs through an algorithm. I don't need a guy. So I run it through that. Number 3, I can then take that, if I can make that and turn it into a nonlinear predictive forward predictive model so that I can predict what will happen to that building next. Then, of course, number 3, I can assess the risk using something called incremental dynamic analysis, where you run a series of earthquakes through, and you keep incrementing the magnitude, and you look at the response. We know what kinds of responses, what kinds of interstory drift, the relative motion between the ceiling and the floor, lead towards collapse, or at risk of collapse, or whatever condition you choose to put on it. And that way, you know by the size of the earthquake, because we have people like Brendan Bradley and many others around New Zealand doing a lot of modeling on what's the risk and the size of an earthquake. I can tell you exactly the risk over the next week, months, years of collapse, of major damage, given an aftershock of any given size, and we know the likelihood of aftershocks in size. So that's the idea, basically about a doctor for the building, but also a predictive doctor. So what is this hysteresis loop? We've seen some before. Alessandro showed some. It's the amount of force versus the amount of deflection on this axis. And so what happens is buildings go up, they yield, and then they return, maybe to center. But we see this every day. Every time you breathe, your lungs go through a hysteresis loop. We use similar technologies to diagnose breast cancer in women non-invasively without pain, compression, or x-rays. It's a whole separate UC Connect. It's a little pitched back to Michaela in the back. So what if I measure these using simple sensors and a bit of knowledge about the mass of the structure, and I know the ground's motion because I'm measuring as it happens, and what if I track them over time? What happens? So most buildings, you'd like to remain linear. You have sort of this. Concrete buildings, in these big examples you saw here, they have pinching and degrading. So actually the concrete cracks, Alessandro had many pictures where the base of the bridge pier, all the concrete spalled away to the steel. So it actually starts out, your stiffness almost disappears until you start compressing more concrete again, and then the stiffness goes up, but it's still much lower than before. So it starts out with a steep slope, and it just falls off. So we can just track that. We monitor these. We use a simple statistical algorithm to fit some basic lines to it, and we can monitor every element, elastic, inelastic, and any other element of stiffness, so we can track it over time. Even if it's degrading and that overall stiffness of that loop, like this over here, is just falling over. It's as simple as that. No advanced math, no advanced professor really required, although I was totally necessary myself. So, does it work? I mean, that's finally the bottom line. Does it work? I can sit here and talk all day, and I'm a distinguished professor, not just any professor, so of course it works. Maybe. Anyway, this is E-defense. So Alessandro showed us a big shake table. Geoff showed us a bigger shake table. Got the biggest shake table. All right, so this is E-defense. You can shake. This is 2, 3-story sort of standardized apartment structures being tested in Japan. It cost $250,000 just to warm up the hydraulics on this, I'm told, anyway. I was really fortunate that we had some Japanese collaborators who thought it was worthwhile to pay for this. So you have, in the Y and the X directions, you have various sized earthquakes. A peak ground acceleration, 0.11 is pretty small, 0.62 is pretty bloody large. So, we'll look at some of these. There's 6 of them. These are the sort of 2 biggest ones there. Does it work in the X and the Y direction? It also shakes vertically. So here's the X direction. And so you have your first 3 stories, story 3, story 2, story 1. I agree it should go story 1, story 2, story 3, but this is sort of it's the way we do things in structural engineering, and we know it's backwards, but we like it that way. So in the first event, it's pretty small. There's a little bit of a drop in stiffness, Slightly more in the second one, like another small aftershock, slightly more. There's the first big one, and it's massive, particularly in the second story. It's lost almost half its stiffness. And then the last one. And the dashed lines is modeling up to the modeling and the prediction. This is a nicely constructed test structure, instrumented everywhere. Does it work? Part 2, this is the other direction, and yes, it does. The big thing to see is that between every event, it ends here, it starts here, it ends here, it starts at almost the same place, same thing, right? That level of continuity has not been demonstrated by any SHM algorithm anywhere in the world at any time to this date. So you could do, with just loss of stiffness, you can do rapid damage tests. And if I lost 0 to 10%, you can go right back in. 10 to 20%, maybe, but we should inspect and patch it. 20 to 40, moderate damage. 40 to 70, major damage. Come back. That, number 4, Toshin Seibu, that's major damage. You're not going back in that. And then over 70, somewhere in there is collapse or a huge risk of collapse. So it's real time. I can give you that answer within 10 seconds after an earthquake. But how can I predict from this result? I know what happened. How do I go from what happened to what's coming next? First, a little aside. This is the BNZ building near the waterfront in Wellington. It was only built in 2009-10, I believe. It had sensors in it, 15, courtesy of GNS. And it went through 3 events over the course of several years: a Seddon earthquake in 2013, Lake Grasmere, smaller in 2013 as well, not too far afterwards, 3 weeks, 4 weeks. And Kaikoura, which we all remember down here, is a sort of big rolling event, which was a little bit bigger up there, although that's 7.8 magnitude at the epicenter. So it's monitored quite heavily. And we've talked about cost here. Geoff has pointed out that it's 0.2, 0.3, 0.4% of building cost to put in devices. Pretty similar for Alessandro's work. We're looking here at 0.1% or less. So what if I said to you, you could have all of their stuff and my stuff for 0.4%, 0.5% of building cost? For the average sort of Christchurch house, where I'm going to round that down to $500,000, you'd be looking at, what, $2,000, $2,500? You ask people, what would you pay to have this be, you know, really earthquake-proof, really safe? And the answer is, you know, a heck of a lot more than that. And then when it comes time to buy it, they all sort of walk away, as Geoff and Alessandro have mentioned too. Oh, it's pretty expensive. I don't know. So there's my bit of argument for today. So here are the 3 events. Again, we have nice continuity between the events. Just looking in one direction here, although we have motions in every direction. Consistent tracking. Earthquake number 1, the first story, which I've put on the bottom now where it belongs, that's a 40+% loss of stiffness in both directions, as it turns out. It was over 70% or close to 70% by the end of earthquake number 3. And if you think about it, stiffness works like standing on the floor, right? So, you know, we've seen this example. I sway back and forth. You know, if you bust up my ribs a little bit, I lose a little bit of stiffness up here, right? But it's the stiffness from the knees down, the first story, that keep me rooted to the ground and standing up straight. So, better information. So after the first event, the reports anyway, we haven't seen the detailed damage reports. The reports were, well, cosmetic damage, minor patching, and they went out of the building, though, for several months. The second event, there was no one in the building actually at the time. Oh, same thing, minor cosmetic stuff. The third event, 70% loss of stiffness. They had concrete spall. I said, oh, we're going to have to demolish it. And even then, it was kind of disputed and fought between engineering experts, and lawyers got wealthy. So you can see some big damage, and then further relatively big damage. You're well into that 40 to 70%. The reduction here is 53% in this direction. Here's a hysteresis loop, and you can see it starts out almost vertical, just buried in there. And pretty quickly, the loops get wider and go like that. Further and further, and you can see the overall slope here after the damage is higher than it is there. And as that slope falls over, the building falls over is the way to think about that. You're well into that rebuild and demolish a structure, which is finally what happened to a 10-year-old-ish building. So how do I turn that into the prediction forward? So I can take this guy here, the physical building. I can start to do the structural health monitoring. I can turn measured data into ones and zeros, and I can then turn that hopefully into a predictive, fully fledged model, a digital clone of the original guy, able to predict or do what would happen next. So I take these SHM results, I add them to machine learning and simulation, and I come up with a nonlinear model that I feel will best predict without going into what's under the hood. So best predict what will happen next. Again, does it work? So again, we'll go back to our friends in Japan. I will do the SHM on this event where we had that major damage, and I will predict forward to this relatively small event and then to this really large event. And I will simulate them, and I'll see, did I get exactly what they got on the shake table? Right? Proof is in the pudding. Money where the mouth is, all those words. And here we go. So here's the first event. And there is what I would re-simulate for that. And you can see the blue lines are the measured. The red are the actual model. It's pretty close. Still pretty close to here. And we mostly care about the relatively large motions, the peak motions. The small stuff isn't of major concern. And then a large event, 2 events later. So that could be that aftershock, 40 minutes to 3 hours after. Again, I'm predicting quite well, if slightly conservatively here, the peak values. I can know the amount of extra damage. I can capture that stiffness loss because those peak values, that good match, come from capturing that future stiffness loss, the one that I didn't know about yet. So I didn't pre-guess, I didn't pre-model. All right? If I can know that that next 20% of original stiffness loss is coming, and I can model and capture that, then I would get this exactly so, including the loss of frequency as the period increases. So that's a digital clone. From that, I can predict the likelihood of collapse for that structure using well-known computational methods. It might take an extra 10 minutes, 20 minutes at most. Depends on how good the software you want to run is. That's a digital service. It's that simple. So you could then take this and say, well, if I'm watching this building, then I know the other buildings that are similar around it. I can probably tell you, not with the same kind of accuracy, but I can probably tell you what their status is. We call that wide area structural health monitoring. And you could start monitoring with selected canary buildings every second, third, fifth, whatever the number might be. It's low cost, 0.1% of building cost or less. You could start monitoring what was going on. And you'd have a very good idea of what had happened in that city. Much better information leads to much better decisions, leads to much more rapid decisions, leads to more rapid and more optimal dispersion of resources. To a rebuild leads to far faster both recovery of the city and economic recovery overall. Why is this necessary if we have these great devices? Because, well, in this city it's a bit hard, but in most cities, the buildings that will be here 40 years from now, they're 80% of the ones that are here right now. As we rebuild this city, it will take time to see that changeover. So a brief pause for some reflection and some thoughts. I'll say a digital clone in the future and try to link it all together from what we've seen. We have the future really of buildings, our future of SAHM. The problem, engineering input is often not available for days, weeks, months. And it may be highly variable in content. How stressed is your engineer? What if I had an automated algorithm? I don't need a guy. Problem, inaccurate assessment devalues post-event decision-making. Assessment, I'm sure for the BNZ building, for many buildings, they follow standard protocol. You go in, you make certain assessments. You know that certain kinds of indications are a certain level of damage. You follow the rules. You know, no one's doing wrong here, right? It's simply not up to the task. It's not up to what you can get from sensors and data used properly. So accuracy, we can deliver that through algorithms. Building collapse can happen in the future. Further damage, how safe is this building? Prediction and digital clones are our answer to that. And then the problem, earthquake input is unpredictable. Seismic response, as we've heard, and the seismic input itself is highly variable. The methods are robust to all kinds of earthquakes. Once you enter that prediction phase, I can simulate a wide range, as Jeff Rodgers showed you, all sorts of earthquakes. We don't know which one or what type of one is coming next, but we can look at all of them. It's just computer time. It's just a little bit of electrons and hardly any power. So that's the digital clone future. And I would say we should get to questions by pointing out this is a large earthquake-prone city. We'll be voting about some people that are just off to the left side of this picture in the next coming weeks. I urge everyone to vote as well. And we don't have much in the way of buildings with advanced devices or with advanced monitoring of any form. So with that, I'd like to bring both speakers back up to the stage, and if you guys have any questions, we'd be happy to answer them. Yes, sir.
With the stiffness factor, for the stiffness factor, do you go on your design criteria of the stiffness of the building, or do you somehow measure that before you actually put your sensors in to find out what reduction there is?
So for structural health monitoring,
you've got to measure it against something.
Yeah, so you will have, to measure deflection, what you have is accelerometers in there. You can double integrate those and get, or use other sensors to get the actual deflection. If you know within reasonable accuracy the mass, which is generally well predictable in civil engineering, you can get the input force from the ground motion, at which point on that force, on that deflection, I can get stiffness out to an exact value. In experimental lab tests that we've done with pretty much the same crowd at Tongji, where you know everything, you custom built it, you can calculate the fresh built structure, and you can calculate really what should happen, and we get that number back out. Because we know the mass, we know exactly that. Libraries, for example, are notorious for having variable mass. There's people in it, and they're sort of guessing, well, there's books and stuff in it, and that's kind of known, but you know, how many books are there? The heavy books with the heavy paper, and you know, one book doesn't matter, but when you have 1 million volumes, suddenly it all adds up. but we get an exact value. So that's a deterministic value that is generally pretty close. As close as we know the mass.
Why I asked that question is, when we're installing a crane, what has actually been calculated for the stiffness, we load test it and find out its deflection, but you can't really do that once you've built the building before you put your monitors in.
No, you can't. So it's part of that construction variability. You know, was the concrete allowed to set right? Was it a human? Yeah, now I gotta switch it on. It's the switch button, not the one that says push. Oh, that's loud. So that's what's called long axis and feedback. So let's just go to, I'll stand over here. Come on up, guys. And we'll get rid of that. In a different job long ago, we used to model that as well. When you get it wrong and you're wearing the earpiece, it's really bad. So come on up, don't be shy. So buildings aren't always built exactly so. It can be any number of factors in and out of the control of the people doing the construction. So you don't quite know. The first time you even get a modest shake, we would be able to give you a number. In theory, it's been designed, and look, there were a couple of tragic collapses, but the vast majority of buildings performed pretty much exactly as expected. Many were demolished afterwards because people were uncertain about how much damage had gone through, but they performed as expected in terms of life safety and the motion that seemed evident afterwards. So at that point, you do need something to get it going, but you don't. We can give you a pretty exact value after that.
I think if I can add on this, I mean, you can't really obviously test the buildings that you said. It's easy to do on the crane, but you can't do on a building. But the idea is that, as Geoff was showing, is that you build up those digital clones and you build robustness on those models such that even though you haven't tested your building, you are in a position to assume that the stiffness is dropping in the way you think is going to happen to the real building. But there are complexities because each building is different. So, and you know, you change the detailing. But I think we are in a good position to even to predict without having the need to have the testing on the specific building. I don't know, just, yeah.
Have you managed to get any accelerometers or digital devices in any of the structures that you've talked about to monitor performance?
I believe there's a small handful in this very building. There were some temporarily in Christchurch Women's Hospital. We did some work on that after the 2011 event, and Geoff might know more. Yeah,
so in this building there's some accelerometers on the foundation level. There's also 2 accelerometers in the penthouse roof up above us, and there's also some displacement gauges across the devices. So there is, you know, well, it's not a rich data set compared with what you might do. Like that test in China, we had 380 channels of data coming off that. We've got more like 15 in this building, but it's 15 more than most buildings have.
And are we ready for me to start asking the clients that I have to start putting these things in buildings now?
Please do.
But I think there is another element here. Like, obviously, if you think about the building, you have a lot of columns, you have a lot of beams, you have a lot of floors. The challenge is actually to find the critical elements in a way that you optimize the way you actually position those devices, because otherwise the cost can even be more than 0.3%, and that is the key thing. And because otherwise it will be very difficult to fly. So the challenge is, like we were showing those devices, right? If we can measure easily what is the deformation, the displacement of the single device, it could even be that after the earthquake, you don't need to do anything. So our resilience function is going to be 100%. But the key thing is not throwing sensors everywhere in a building, otherwise your client will say, sorry, it's too expensive.
Could you share with us safety features of the Otera viaduct, please? I've always wondered about that every time I
That's a tough question. I think, yeah, that's everyone is going away. So yeah. No, I think the Otira viaduct actually, in a way, has been designed with is a conventional design. So if there is going to be an earthquake, you will have the damage, potential damage, happening at the bottom of the bridge columns. Having said that, the way has been designed in a way that the coefficient, the ductility that the structure can have is not extensive. So basically means it's going to displace a lot. I think it's up to 400 millimeters at the top for a big earthquake event. But the pier, because it's tall, is actually flexible enough to limit the damage at the bottom. So we will not expecting to have extensive damage, but there will be some damage. And on top of that, the Otira also have, when you look, that it's a beautiful bridge, right? It's a balanced cantilever, the longest balanced cantilever built like, with a column on two sides going like this. It's the longest, it's 124 meter span, and is the longest balanced cantilever bridge built in the South Hemisphere. But there's also the challenge of being close to the Alpine Fort, designed with 0.5 G, and then there is like this big potential slip failure, which could actually hit the bridge. So they put also some barriers. So it's quite challenging, but I think in a way it's been designed quite conservatively, but I will say it's not like a low damage technology, but I will not expect extensive damage on the bridge. So you can drive safely to the West Coast.
So going through the Christchurch earthquakes, we saw that liquefaction is a very important part of this story. Can you also deal with that, or how do you estimate the damage by liquefaction on top of the shaking?
So but my voice is so big. So for liquefaction, so what happens then is that the building, if you imagine that the entire area liquefies to soup, so to speak, the entire building rotates rigidly, so it's a bit like a rocking structure in mud. So you get excessive deflection. That excessive deflection, when the building rotates rigidly, now the floors are a bit offset and they start to pull down, and you will get damage to that structure. So what we would see from structural health monitoring is we would see that uplift, and we would see the vertical load, we would see the damage due to that rotation, and we would see the loss of stiffness both in the bottom spring, if you will, due to that rigid motion, as well, which is the foundation of the soil structure interaction, as well as any damage that happened to the structure with it. Probably the best case in point from the big earthquakes here would have been the Grand Chancellor. So my office window sort of faced out that way at that time, and you could look down and you see the skyline before it got torn down, and it's building here, building here, building here, and the Grand Chancellor. So there you see something about the foundation and its interaction there, and actually moved rigidly. So we can detect that, and we can quantify that. Usually you see more of that if probably in older structures where pile design and foundation design wasn't up to modern standards or expectations. The foundation is the most expensive part, so if something is cut to the limit, it's usually that. But in essence, from structural health monitoring, we can deal with that. As you saw with Jeff Rodgers, he mentioned for the building in San Francisco, which is out towards an area of soft soil, where you can have these kinds of events. In fact, the big news there until fires was lawsuits about tall apartment buildings that were starting to lean and sink. So they've got there actually the dissipation between the foundation piles and the foundation. So you'll see that in the mitigation side, hopefully through good or over design of foundations, although that's another cost that people don't like to wear, as well as through how you use devices, and we can see that in the SHM from the measurements, if you have them in the right spot.
So one ongoing project at the moment that I'm not involved in, but it's through QuakeCore. So QuakeCore is a Centre of Research Excellence funded by TEC, hosted at UC, but collaboratively throughout the country. They've actually got a project going on at the moment with monitoring the Ferrari Bridge. So there's been a new bridge built, demolishing the old one, and they're doing snapback tests on some of the bridge columns, then also digging out some of the piles, providing different lateral support to the piles, and actually getting quite a good data. It could be quite a really unique, valuable data set in terms of what the overall system stiffness is based upon how much support exists in the soil around the piles as well. So that's in case is basically digging it out, but it will also be a good analogy for liquefaction as well.
I would say it's very difficult to monitor liquefaction in interaction within the interaction of the structure, because usually when you do those analyses, especially for bridge design, you have a big scatter. You always look at upper bound, lower bound properties of the soil, because we have a big uncertainties. So it would be certainly more challenging for Geoff actually to predict, fully predict the interaction with liquefaction. But obviously, for example, you think about a new building, a building like this, you do mitigation strategies to avoid to have any permanent displacement induced by liquefaction. But on an existing structure, this certainly is very challenging.
I think it's worth pointing out, liquefaction damage, one way to look at it in earthquakes is often, it's a bit of a function of history sometimes how cities grow, but it's also a function of urban pressure. So cities want to grow, so then they start moving to land that even 150 years ago people knew probably wasn't the best even before they were really aware of earthquakes. So you get pressures to build. There are chunks of the red zone that had only been built up in the handful of years before 2011. There's a lot of pressure for housing. People didn't want to grow outwards, which it now has to satellite towns. So you see liquefaction. Singapore, which might be subject to low and long wave earthquakes, is a city-state that has been actually truly growing over the years through refill. The same with parts of San Francisco. And so under pressure, people take these choices. They often don't want to pay quite as much as what would really be necessary to make it truly safe and rock solid. And so there are a lot of interesting, I guess, if you will, political and economic interactions that cause that to be a problem. In theory, you would just build away from those spaces, especially now where it's easy for us to test and figure out what's prone and what's not. Any other questions? Yes?
A lot of the discussion you've had is about very large construction, capital-intensive works with qualified engineers and all that sort of stuff. What about at the micro scale where we're talking about house building and the utility where most people are interfacing with their life investment? What sort of utility do we have in the knowledge that we've got? We do apply to these kind of buildings. How can we build them safer?
So in general, lower is safer. So houses, here's something that'll get me kicked out quickly. Houses often don't suffer huge amounts of irreparable damage, although there are plenty near all the streams and creeks, and I know insurance issues have exacerbated that to the moon and beyond. So they're generally pretty safe. That said, I do a lot of running, and when I go around running, watch various new houses houses go down and go up, and I'm increasingly seeing steel. So you'll see at least a handful of steel I-beams connected by wooden frames, and they're should provide more than enough resilience at that level. If you said to me, Geoff, I really want my house base isolated, I'd be like, all right, that's really cool, and be happy to help out with that. But it's a very nice to have. It shouldn't be a necessity in terms of the way we can build houses. Once you start getting up to 3-4 story apartments, say out towards Sumner, Red Cliffs, where you're getting into that sandy soil right by the coast there, that's another very interesting question. And that's actually kind of what was being tested in Japan. So in theory, I'd like to say you shouldn't have to worry in a house. Clearly that's not been the case. There are something like 220,000 houses in the sort of greater Christchurch, some such number that I'm sure is not right, but might be close. And there are, the red zone and liquefaction is a major issue, and that's a liquefaction. Maybe we shouldn't have been there, but most houses were not damaged heavily. right? We hear a lot about those that were, and I have a huge amount of sympathy and a couple close friends in various places where even today they're just getting settled. And the amount of aggravation over that is, worth 100,000 undamaged houses probably. But that's a political and policy question, I'd say, probably more than an engineering one. I'm not sure if that's an answer anybody wanted to hear.
Certainly, as Geoff was saying, this application can be extended to medium density houses. Like we're talking about 3, 4, 5 stories building. One thing that probably I wouldn't be doing if if I'm an owner, we will not probably use those devices, like those fancy devices, because as Geoff was saying, that the houses and these, short story building were performing extremely well. But what we are working now with one project, we are actually trying to do a sort of low-cost base isolation using the rubber, the waste of the rubber comes from the tires, and putting it underneath the foundation as a sort of low-cost base isolation. But again, I will not be doing for a single-story house, although we spend a lot of money for mitigation liquefaction. So we have, if you have a house in a TC3 land, you do these rebraft or systems to avoid the permanent displacement. But in terms of ground shaking, probably is only an application that goes for medium density houses, where we're talking about maybe 3 or 4 stories buildings. So it's mainly probably a problem from Auckland and Wellington. I don't know if Christchurch, we don't have many of those type of buildings.
If I was building a house now, I'd probably have a steel frame with wood framing in between major sections.
A typical car today has many accelerometers in
Mm-hmm.
the airbags.
Yep.
My camera in my car has an accelerometer in it itself.
Yep.
It was $100 with a camera
Mm-hmm.
and really useful tool. Is the utility in having acceleration detection across the fabric of the city now that we know we learned so much from this?
I would certainly say so. So accelerometers in cars actually started out when I started my career for the most part. And then they rapidly commoditized from something that was TRW, could make a lot of money on, to something they were hard to get out of the business of. And yet we see cars that are 5, 10 years old run into things and airbags deploy. So clearly they're still working, they're still on. The amount of cost that people would say for seismic accelerometers and a special case and one-offs and very low numbers produced, very, very low numbers produced, they're quite expensive. But if I said, well, we're going to do this in the city and I need $1 million over 5 years to deploy, just as a roundish number, right? Prices would come down, you could readily imagine. I would say so. But, I would live for data like that. GNS, I'm not sure how many buildings I monitor.
So when the 2011 earthquake happened, there was 4 main strong motion sites within Christchurch. There was the Botanic Gardens, the Cathedral College by the Catholic Basilica, Christchurch Hospital, and Resthaven in Colombo Street. There's now actually Canterbury Seismic Instruments and the City Council have gone through and put in the Smart Cities Array. So essentially within the main 4 avenues, basically every intersection has an accelerometer in it. We're actually using the traffic light control boxes, which are an ideal thing with power, internet, everything you need already in there. So we've gone from 4 sensors. 18 months ago, we wouldn't actually really have had any more data had we had another earthquake than we had in 2011. Whereas now we're up to about 80 sensors within the 4 avenues as opposed to 4 last time. So I think that is a hugely valuable asset in terms of if we have another earthquake, perhaps not having to paint such a broad brush and red zone the whole city. We actually block by block inference of what ground shakings were, ground shaking was likely to be, and much more informed decisions on how to respond. So I think that's been installed in Christchurch, and they're also rolling that out in Wellington at the moment. So I think that's going to be really valuable if, fingers crossed, we don't, but if we do have another earthquake.
So my take is a bit different. I actually don't care what happens in the intersection. I care what happens in the building that I'm in. And you'd like to see a lot more. There is a belief sometimes in New Zealand that, a digital business, a services business, you can't make money on that. There's not a patent. And then people write that down on your grant request or anything else, and they go home and they watch your favorite show on Netflix.
So I guess, and that's so Canterbury Seismic, they've always traditionally the business model was pay $5,000 for the system and get it installed. They're actually moving more towards options of having it as a service. So they own the instrument, they install it, they service it, and then you just pay sort of a monthly subscription to have access to the data. So then I guess from an accounting point of view becomes OPEX rather than CAPEX, and that has all sorts of implications which accountants love.
We need to close. Do you have any other questions? No, because they are kicking us. Okay, otherwise we don't want to sleep in this beautiful and safe building, right? So
They've got game boards over there.
so, anyway, I think we have to close up. I don't know if we have to.
Look, just some closing words. Thank you all for coming. Really appreciate it. I'd like to say that Canterbury is doing a lot of research. I think sometimes it doesn't get out to the wider world. So hopefully you've appreciated what you saw here tonight. We all know that Corvette is better than Ferrari. If you take nothing else home, you should take that home. Nothing more from you, sir. And thank you all very much again for attending, and hopefully we'll see you at some future UC Connect. Thank you very much.